In this session, we discuss first the length of a smooth curve, smooth parametric curve. Now, what do we mean by a smooth curve? Suppose we have a function y is equal to f of x. This function is said to be smooth if f dash is continuous. That is, f is differentiable and f is continuous. Then we say the function is smooth. Geometrically, for a smooth curve, at every point, a unique tangent can be drawn. So it is a graph of the function will not have corners like this, or it cannot have a cusp like this. Such a graph, such a function is called a smooth function, or corresponding curve is called a smooth curve. So if we are given a smooth curve, how do we find the length of the smooth curve? So that is what we discuss in this section. Already we are familiar with finding the length of a curve between two points A and B if the curve is given in the parametric, sorry, Cartesian form. It is given by the formula L is equal to integral a to b root of 1 plus f dash x the whole square dx. Here we discuss if the curve is given in the Cartesian form, sorry, parametric form, y is equal to x is equal to ft, y is equal to gt, where a less than or equal to t less than or equal to b, how do we find the length of the curve? So a smooth curve, already I told what is a smooth function. A smooth function of x means it is differentiable at all points. The graph representing the function will not have corners or cusps. Now let us take a function which is given in the parametric form, that is x is equal to t, y is equal to gt, where the parameter interval is the closed interval ab. To find the length of the curve from t equal to a to t is equal to b. So this is the point t is equal to a, that is f of a, g of a, and this is the point fb, gb, vb. Here we are assuming that this curve will not intersect anywhere except the endpoints. That assumption is also made here. Now, first we do is we derive a formula for finding the length of curve in parametric form. First, we divide this parameter interval AB, closed interval AB, into finitely many equal intervals, subintervals of length, say we can say delta t, which is equal to b minus a divided by n, or each interval tk minus 1, tk is of length tk minus tk minus 1. Let it be delta t. Such a way you partition the parameter interval into finitely many subintervals, taking the points t0 is equal to a, t1, t2, etc., tn minus 1, and tn is equal to the right and point b. Now, corresponding to these t0, t1, etc., tn of the closed interval ab, you mark all the points on this curve like p0, p1, p2, p3, etc., pn, where p0 is equal to ft0, g0, gt0, p1 is ft1, gt1, and so on. Now join all these points p0, p1, p2, etc. by line segments so that we will get a polygonal curve. Polygonal curve. So joining these points p0, etc., pn, we get a polygonal curve. We'll find the length of the polygonal curve first. The length of the polygonal curve is the sum of the line segments joining each point p0, p1, p1, p2 like that. And the length, for example, pk minus 1 pk is obtained by the formula root of ftk minus ftk minus 1 whole square plus gtk minus gtk minus 1 the whole square. Therefore, the total length of this polygonal curve is sum of all these line segments, which is sigma k is equal to 110 root of ftk minus ftk minus 1 whole square plus gtk minus gtk minus 1 the whole square. But ftk minus ftk minus 1 you can write in the form f dash tk star into tk minus tk minus, since f is continuous and also differentiable. In the interval, if you take tk minus 1 tk, you can see that by applying mean value theorem, Applying mean value theorem of the function f on the interval tk minus 1 tk, there exists a point you can find. There exists a point you can tk star such that f tk minus f tk minus 1 is equal to f dash tk star into tk minus tk minus. Similarly, g is continuous and also differentiable in the interval tk minus 1 tk, and therefore there exists a tk double star in the interval tk minus 1 tk, satisfying the condition gtk minus gtk minus 1 is equal to g dash tk double star into tk minus tk minus. And tk minus tk minus is nothing but the delta t, length of the interval that you have taken. Therefore, replacing this ftk minus 1 by this expression and gtk minus 1 by g dash tk double star into tk minus 1, then the formula for L is reduced to this type. Sigma k is equal to 1 root of f dash tk star square plus g dash tk double star square delta t, where delta t is tk minus tk minus 1. And it is uniform throughout the interval. This delta t is constant. Constant in the sense that the length of the interval is the same. And this is actually a Riemann sum. No? When n becomes larger and larger, that is the number of partitions of this interval AB is, if this number of intervals is becoming larger and larger, what happens is the line segments that we are getting is up almost to the curve. So the polygonal curve is tending to this given curve if this number of n intervals is very large. So therefore, the length of the polygonal, the length of this smooth curve is obtained by taking the limit of this sum by the idea of Riemann theory of integration. So limit n tends to infinity of sigma k is equal to 110 root of f dash tk star square plus g dash tk star double star square delta t reduced to an integral of the type integral to be root of f dash t square plus g dash t square dt. So this is the Riemann theory. According to Riemann theory, this sum is called Riemann sum, and this Riemann sum tends to an integral of this type. It's called Riemann integral. Integral to be root of f dash t square plus g dash t square dt. And this is the formula that we are using for finding the length of a polygonal, length of a smooth curve. This f dash t square is nothing but dx by dt, you can write. So dx by dt the whole square plus dy by dt the whole square root of that integral a to b dt. And this formula is taken for finding the length of smooth curve if it is given in the parametric form. So hence we have this theorem. If C is a smooth curve represented by the parametric equation x equal to ft and y is equal to gt with the parameter only b, then the length of the interval, the length of the curve is obtained by integral a to b root of dx by dt whole square plus dy by dt whole square dt. Now we take an example. Suppose we have a cycloid and one arch, length of one arch we have to find. Now one arch is obtained by revolving a circle of radius, some radius, fixing a point on the wheel. It's like a circle. Suppose we have a circle with a fixed point. When it is moving on the line, we will get a cycloid. And when this circle rotates completely once, we get one arch. So one arch is obtained from theta, varies from 0 to 2 pi. 0 to 2 pi. And so therefore, the limit of the integration in the formula of finding the length of a smooth curve is 0 and 2 pi. And therefore, the length of the one arch of the cycloid is obtained by integral 0 to 2 pi square root of dx by dt the whole square, dx by d theta the whole square plus dy by d theta the whole square d theta. Then you have to find dx by d theta and dy by d theta from the given parametric functions x equal to into theta minus sin theta, y equal to n1 minus cos theta. Just take the derivative. We have dx by d theta, you can write as a into 1 minus cos theta, and dy by d theta is equal to sin theta by differentiating with respect to theta. Then substituting this in the formula, we get the length is 0 to 2 pi, square root of dx by d theta is a into 1 minus cos theta the whole square plus dy by d theta is a sin theta whole square. Simplifying this, what is under this square root sign is reduced to 2 into 1 minus cos theta d theta because we have sin square theta plus cos square theta equal to 1. Therefore, the term a comes out. So, a into integral 0 to 2 pi root of 2 into 1 minus cos theta. To integrate this 1 minus cos theta, you have to express this in terms of powers. For that, we use the result sin square x is equal to 1 by 2 into 1 minus cos 2x the result. Putting theta is equal to 2x here, we get 1 minus cos theta is equal to 2 sin square theta by 2. So in this place 1 minus cos theta, just substitute 2 sin square theta by 2 for integrating that. Thus we have L is equal to a into integral 0 to 2 pi square root of, and 1 minus cos theta is 2 sin square theta, that becomes 4, 2 into 2 sin square theta, that is 4 sin square theta by 2 d theta, which is equal to 2a into integral 0 to pi sin theta by 2 d theta. Now on integration, you can see that it is 8a. So this is the result. This is actually the length of one arch of the cycloid. One arch of the cycloid. Length of one arch of the cycloid is 8a, where the curve is a into theta minus sin theta, y is equal to a into 1 minus cos theta. Now we will go to another concept called area of surface of revolution. Now, how do we get a surface? By rotating a curve about some line. You can see that suppose we have a line here and a curve like this. When it is rotated about this line, there forms actually a surface. And what is the surface area of is the surface we are getting, and what is the surface area, that is in Cartesian form we have already a formula. If y, sorry, yes, if y is equal to f of x, suppose when base of the curve from A to B, if it is rotated about x-axis, x-axis, we get a surface, and the surface is obtained. The surface area is obtained by the formula 2 pi integral A to B y ds, where ds is equal to square root of d 1 plus dy by dx the whole square dx in the case of Cartesian form. Okay. Similarly, if it is rotated about the x-axis, the formula is 2 pi into integral a to b x ds. X ds. The ds is square root of 1 plus dy by dx whole square dx. Now, in the parametric form, if it is given, suppose we have a curve like this, f is equal to ft, y is equal to gt. When it is rotated, that forms a surface like this. Surface like this. Suppose it is rotated about x-axis, we get a surface like this. And the surface area is given by integral a to b 2 pi y ds, since it is rotated about x-axis, and where ds is equal to square root of dx by dt whole square plus dy by dt whole square dt. Therefore, the formula is actually reduced to surface area is 2 pi, you can take outside, integral a to b y ds. Y means square root of dx by dt the whole square plus dy by dt the whole square dt. So this is the formula for finding the surface area of revolution of a curve when it revolves about the x-axis. Similarly, when it revolves about the y-axis, suppose it is rotated about the y-axis, a different surface will get, and its area will be, surface area will be 2 pi integral a to b, instead of y it will be x ds, which is the same ds dx by dt the whole square plus dy by dt the whole square. So this is the formula we have. If C is a smooth curve, when it is rotated about the x-axis, we get a surface area like this. Similarly, if it is rotated about y-axis, we get formula 2 pi integral to the x in here 2 pi y square root of. Okay, now we'll take a problem how to find the surface area of a sphere. Now, sphere of radius r. To find the surface area of a sphere of radius r. We know a sphere is obtained by, suppose we have a sphere is obtained by rotating a semicircle. No need of taking the whole circle. Just rotate the semicircle about x-axis, you get a sphere. A semicircle means this equation, x is equal, suppose it is of radius, here it is radius r, and therefore the parametric equation of a circle is x is equal to r cos theta y is equal to r sine theta, where theta varies from 0 to pi here, 0 to pi, 0 to pi. Okay. The formula for finding the surface area is equal to integral 0 to pi 2 pi y ds, where ds is equal to square root of dx by d theta the whole square plus dy by d theta the whole square. So this is a formula. Now you find the dx by dt and dy by dt. Here actually x is equal to r cos t. X is equal to r cos t. So what is, sorry, r cos t? Then dx by dt is equal to, r is constant, derivative of cos t minus sin t. So it is minus r sin t. Similarly, y is equal to r sin t. Therefore, dy by dt is equal to r cos t. So substituting in the place of dx by dt and dy by dt, respectively minus r sin t and r cos t, we get like this. 2 pi integral 0 to pi y is r sin t, root of dx by dt whole square minus r sin t whole square plus r cos t whole square. Then 2 pi r is constant, 2 pi r we are integrating with respect to t, so r is constant here. 2 pi r integral 0 to pi sin t into root of r square sin square t plus cos square t. R square you can take outside. So 2 pi r square, and this is 1 sin t. So integral of sin t is minus cos t between 0 and pi. So you get 4 pi r square. You know the surface area of a sphere of radius r is 4 pi r square. So that is obtained by the rule, by the formula 2 pi integral a to b y ds. By using this formula, we can find the wall surface area of a sphere of radius r. Okay, thank you. With that, so here we discuss some calculus of parametric equations. Like earlier, we discussed length of curve. Here, length of curve, and also the surface area of revolution of a parametric curve. Thank you. Thank you very much.